Okay, today we're going to talk about collecting a gas over water, which is a partial pressure problem. And often this seems to cause trouble for students. It's really not too difficult, but it just takes a little bit of understanding, and I think that it'll be fairly easy for you. So let me open up a problem here, and we'll talk about how it works. So collecting a gas over water is a fairly common technique when we want to trap a gas that's made by reaction or something like that. So basically the way that it works, if you can see here, let's pretend this tube is connected to a reaction of some sort, and that reaction is generating oxygen gas. So the oxygen would flow through the tube and then up into a container that is initially full of water. So as the oxygen bubbles up in through the water, it replaces the water with gas. And so at the end, you have a certain amount of gas that is trapped in this bottle. And presumably there would be some sort of graduations on the bottle so you could actually read the volume of gas that you have collected or trapped. Now, the pressure inside of this container would be the same, pretty much the same, depending on the difference in the water height here, but pretty much the same as the pressure of your room outside. So if you know your room pressure, then you can use that pressure for your calculations on your gas inside your container. Now, one issue with collecting a gas over water like this is that water basically produces water vapor. So inside of your container, you would not only have oxygen gas, you would also have water vapor. So we have to figure out how to separate those two and understand how to pull just the oxygen gas out so you can do the calculations on that. And it's fairly straightforward. That's where partial pressures come in. So let's take a look at the problem that we have over here. So if a student collects 400 milliliters of oxygen gas over water, what would be the total mass of oxygen collected at room temperature, which is 21 Celsius, and standard pressure? Okay, so let's look at this problem and figure out how we can answer this. Now we know we have 400 milliliters of our oxygen gas slash water vapor mixture that we've collected. So, and we also know that we have standard pressure. Now, standard pressure is 1 atm. It's also 760 millimeters of mercury, which also equals 760 torr. So now, in order to do this, you need to have a table that tells you the vapor pressure at various temperatures, and we have one of those down here. So basically, we know we're at 21 Celsius. So if we find 21 Celsius on our table, we know that the vapor pressure of water at 21 Celsius is 18.7 torr. So notice also that as the temperature increases, your vapor pressure increases all the way up to 100 degrees Celsius, where your vapor pressure equals 760 torr, which happens to be standard pressure. If you recall back a couple of chapters ago, we were talking about vapor pressure and how a boiling point of a liquid is when the vapor pressure equals the atmospheric pressure. So basically you can see here at 100 degrees Celsius, which is the boiling point of water, the vapor pressure of water is 760 torr, which is standard atmospheric pressure. Just a little review, not really super relevant to this problem, but just kind of a reminder of how that works. Now let's look back. We have 18.7 torr of pressure being generated by our water vapor. And the room is at standard pressure. So we know the formula for this is PT equals P1 plus P2, etc. So we can set that up with 760 torr. That's our total pressure, equals the pressure of our oxygen plus the pressure of the H2O, which I'll go ahead and write that in, we know is 18.7 torr. So pretty much just simple subtraction here, and you're going to come up with the pressure of your oxygen equal to 741.3 torr. And of course we had 400 milliliters. So now we have something that we can work with. We have a pressure, we have volume, we have a temperature, and we want to get mass. So since we want to get mass, if you're getting mass or moles, or converting between mass or moles and any of these other parameters like pressure, temperature, etc., you have to use your PV equals nRT formula. So let's start just plugging that in. It'll be fairly straightforward. So my pressure, I use the pressure of my oxygen, which is 741.3. Okay, my volume was 400 milliliters. One thing I would say about this is when you're dealing with this PV equals nRT, you need to make sure that your volume is in liters, not milliliters. So let's go ahead and convert that to liters. And you just divide by 1,000, so it'd be 0.4 liters. All right, equals number of moles. This is not mass, this is number of moles times R, which is a gas constant. And remember, we have several gas constants depending on which situation you have. So in this particular case, we're dealing with torr, which is the same as millimeters of mercury. So let's look down here and we can see, yeah, we've got one for millimeters of mercury. So it's going to be 62.4. So times 62.4 times temperature. Remember, you can't use Celsius, you have to convert to Kelvin. So it would be 21 plus 273. It would be 21. Okay, so now we can just plug that into our calculator, and we're going to get the number of moles equals 0.0162 moles of oxygen gas. Okay, so we're almost there. We've got moles, so now we know that we can convert our moles to grams fairly easily. So it's 16, whoops, it's O2, so it would not be 16 grams per mole, but 32 grams per mole. And then our final, cross that out better, then our final answer is going to be 0.517 grams of oxygen. Okay, hopefully this was pretty straightforward for you and you were able to understand this. If you have any more questions, please let me know. Of course, you don't have to, students always ask me, do you have to remember all the vapor pressures for water? Of course not. You would be provided a table. You just have to know how to use that table and match up the temperature and the pressure, and then subtract it using your partial pressure formula. Okay,